my name is Talley. I'm a first-year master's student under Dr. Gozen, and my research is focused on flow control of microscale direct ink writing. So, direct ink writing is a 3D printing technique where an ambient temperature material is extruded from a nozzle to form a structure. I think we're all fairly familiar with that at this point. So let's focus on flow control and why we care about it. So, accurate features can only be extruded when flow rate is strongly controlled. And some features, such as a corner, for example, require a flow rate decrease to prevent bulging. It is technically possible to avoid flow control if you slow down the entire system and keep a constant low flow rate and just compensate with your motion stage moving at different speeds. However, that often leads to unacceptably low printing speeds, and we are aiming for higher and more feasible printing speeds in industry. So there are two commonly used methods of flow control, which is pressure control, where a pneumatic back pressure is applied to the material in a syringe, causing material to flow out of the nozzle, and plunger control, where a motor is mounted to the plunger of a syringe, which is used to directly drive material out of said syringe. Specifically for plunger control, there's a logical and straightforward relationship between piston position and mass flow rate out of the nozzle, and that is volume displacement. At steady state, flow rate is controlled through the motor speed and can be measured via the pressure sensor. Alternatively, pressure control works by, again, applying pneumatic back pressure, and pneumatic systems are highly accurate and powerful and fairly well explored, and having a fast changing pneumatic system behind it is much easier as opposed to a mechanical system. The problem with this is that at steady state, the pressure is controlled through pneumatic pressure, but you don't have a good relationship to flow rate. And setting up a steady state relationship strictly between pressure and flow rate, and knowing we set the pressure to 90 psi, where will that leave us in flow rate, is not easy to do. So moving forwards, we work with plunger control. So the challenge is that as nozzle sizes decrease, viscous forces and compressibility dominate flow, leading to significant transient behavior. With more complicated inks, we've noticed transients of up to 30 minutes or more with changing a flow rate. In these example plots that are a little bit hard to see, on the left with a 200 micron nozzle, it takes about 7 minutes to respond to halving the speed of the plunger. And on the right, it takes about 1 minute to respond on a 510 micron nozzle of doubling the speed of the plunger. And obviously these are not one-to-one, this is not the same velocity due to very different pressure relationships with different nozzle sizes. But this trend also extrapolates fairly well to more different nozzle sizes. So if you try to go smaller, this trend continues. And if you try to go to different velocity changes, different pressure levels, this trend also continues. So our goal is to devise a method to vary flow rate in real time with significant reduction of transient properties to small nozzles and complex inks, and to ensure that this method is material agnostic and does not require extensive testing and characterization of said materials beforehand. So our current approach is to have our desired flow rate as an input to our system and have a system controller. And we are trying to develop this inverse compressibility block and output a piston acceleration in order to control our system with a feedback of a pressure sensor embedded in the top of the nozzle that will then feed into the system controller and have an active feedback system. So now I'll get into some of the math that we go into for how we get a flow rate through mass conservation, where we start with the Tate equation of state and the mass flux equation, and through fairly simple symbolic manipulation and a few derivatives, we end up with two main equations that we use to one, characterize a local state of a pressure to bulk modulus relationship, and then predict our flow rate out. And that allows us to set up a simple PID loop and sort of relate everything together. And so the process that we do right now is we block the nozzle and compress the ink, collecting a pressure to volume curve. Then we use this equation on the right to find the difference between flow rate and between our current flow rate and our target flow rate. And we use that to have a local solution to compressibility and actively control the system. Issues. So far, this method has been underpredicting flow rate after a volume analysis done after we do some controlled material deposition with our predicted flow rate being steady. And we have a few known causes, but we're looking at a lot of different things right now. And so undissolved air in the ink causes difference in expected behavior. And hyperelastic effects of complex materials are not fully captured in the mathematical basis behind this. And we don't see any of that in the math yet. And I'll get into a little bit of both those. We know that there are more things that we're not looking at yet. We are exploring different paths still. So, entrained air. Due to air being significantly more compressible than any of the current working fluids, undissolved air significantly changes the expected behavior of a system. A lot of models exist for how to isolate the effect of the entrained air from the bulk modulus of specifically hydraulic oil. And so we took some of those models and directly plugged them into our system and got some results that looked really good initially and now look a little bit less good, but I will present them here shortly. And so here on the bottom left, you can see one of the models where the initial K for bulk modulus is the combined bulk modulus, you could say, for both the air that is entrained in the fluid and the liquid that we're working with. Where then we separate it out into X, which is our gas to liquid fraction, and the KL, which is the bulk modulus of the liquid, which we then use with our other equations in order to find what the actual flow rate is out. So, blocking off the nozzle and doing a bunch of different compression tests, specifically with water, to try to do a simple thing that we can then extrapolate out to more complicated materials and work from there, is just looking at the left plot. This looks like a fairly good fit. However, to explain it, the blue dots are the real modulus and the collected values of what they should be. The red dots are the estimated modulus based on our fitted model. And the fitted parameters says that the bulk modulus of water is 1.049 pascals, and that the air volume percentages are between 2.2% and 0.74%. And this was better than a lot of the other things we had when working through this model, because initially a lot of our air predicted percentages or fitted percentages were closer to, well, 10%, 20%, and we know that's not true. Or the bulk modulus was in the range that we know that it's not either. Because the table value for bulk modulus of water is 2.09 e to the 9 pascals, and that is still significantly different than our fitted value. And so we have more to go on this, but this is where we're at right now. As a comparison, we did the same compression test with just part A of a two-part silicone, and the fit is bad. But the air percentages are reasonable, and the bulk modulus is reasonable-ish. And the big thing that I sort of want to point out here is that these curves for the real modulus in blue having a lot more nonlinear behavior for silicone than for water. And right now, we don't have any good explanation for that, looking at all the math. And so then we are sort of getting into our continuing work, where we're trying to understand how the hyperelastic properties of different materials are coming to affect this, especially as we look at what more complicated materials, because obviously we're not trying to use directed grading on water. We're trying to do it for some ceramic materials with maybe we got some particles in there, and there are all sorts of messes and ways, right? And so our continuing work is understanding elastic material behavior under some constrained compression and doing some FEA and COMSOL to compare against experiments that are validating our understanding. And so one of our example experiments here on the right is where we constrain the entire outside of the system in COMSOL with roller mates and add a pressure to the top and see what the stress is on the rest of the part. And this is on a hyperelastic solid rubber to see, does this match up with our experimental data? And there's a little bit more background than that on this one, but I don't really think I have time to get into it today. So that's it.